Okay, good afternoon, everyone. Am I audible?
Yes, sir. Good
Okay,
afternoon.
okay, thank you. So today we will basically continue with the higher order delta function concept. The concept was introduced a bit in the last class, but that is mathematically, mainly mathematically, and you have been asked to do some kind of graphical representation to satisfy that mathematical expression or mathematical relation, at least for one or two order, up to two order of that function. Now today we will actually continue with this, but before that, first let me share the screen with you. Is it okay?
Yes, sir.
Okay. So the way we developed our understanding on the sampling property of delta function and basically the shifting property of delta function, though the proof, the mathematical proof or the derivation have been left as an exercise for you. So you have been asked to consult any book for this mathematical derivation. But anyway, conceptually we developed some understanding regarding the sampling property and shifting property, and the way we did it, if we follow the same procedure, that means the same derivation, if we follow, then as an outcome of that, what actually comes out is something like this. If t, when it is multiplied with the delta prime t minus a, as you can understand, that delta prime is a doublet. It's a first order differentiation or derivative of the delta function. So delta prime t minus a, that should be equals to f of a. This can also be proved actually, but I'm not giving this task to assigning this task to you to consult book or something to for this proof, because you don't need it at all. Just bit mathematics and nothing else. So this minus f prime a delta t minus a. So this is just in formula. Your task will be just to remember this, so that whenever it will be required, you have to just apply it. So as you can understand, the same procedure people actually follow in the books also. The authors follow the same procedure. What is applicable for the derivation of a sampling property of simple delta t, the same procedure if you just follow, you can basically come up with this expression. Just a minute. Okay. Okay, so this expression, so this is nothing but ft, as you can understand, ft, when in general multiply with the delta prime t minus a. In previously, we multiplied it with the delta t minus a. Probably you can remember. Then the result would be equals to f of a into delta t minus a. But instead of that, here, first term you are getting, that is f of a, multiplied with the delta prime t minus a minus f prime a. So that is basically the function ft. For that function, you have to do differentiation once, and then you have to take the value or extract the value or at t equals to a, where delta function exists. Actually, here not the delta function, but the differentiation or the first time differentiation of the delta function exists. Anyway, then it will be multiplied by the delta t minus a, just the delta function itself. So this is just a property. You just take it as an information. It is just a property. You have to remember, and whenever required, you have to just apply it. That's all. So similarly, if another property we actually talked with you, that is regarding the shifting of delta function. So delta function shifting, just you have to do some kind of integration over that. So if you do that again, if you apply the same thing, same procedure over this higher order delta function. So here you can write that it will be from minus infinity to plus infinity, f of t delta n in general, t minus alpha dt, which will be equals to minus 1 to the power n, okay, dn dtn f of t and evaluated at t equals to alpha, where this higher order delta function exists. So it is basically the shifting property of the delta function, or better to say the higher order delta function. But in general, it is true, as you can understand, because if you put the value of n, then you can see that in our case, it was simple delta function without any differentiation. Just a delta function itself was present. So if you put n equals to 0, then you can understand from here, basically this term reduced to actually f of alpha, nothing else. So, but for the higher order functions that use n equals to 1, 2, etc., in general you can write and accordingly you can find out. Please note one thing here, you have to remember this p factor minus 1 to the power n. So when for the odd values of n, always the negative sign will be associated, and for the even values of n, always the positive sign will be associated. That is the point you have to remember, and otherwise rest of the things are easy to remember actually. Anyway, with this basic understanding, it is just a tool for us. Okay, it is just a tool for us. So with this basic understanding, we'll do some little bit mathematics. Suppose, let me clear the screen first. Suppose as an exercise, we're doing a little 1 or 2 examples. Suppose for example number 1, suppose the expression is given 3 t to the power 4 delta t minus 1. This is the expression given to you. Now you have been asked to evaluate this expression or to reduce the expression using the property of the delta function as applicable. Okay, now what you will do actually? So first of all, you first observe that expression very carefully. So you can reduce, you can make this form bit express this bit in a bit reduced form, and if you apply the property of the delta function judiciously. Now the sampling property states that you know that f of t multiplied with the delta t minus a gives you f of a into delta t minus a. Now for this example, for this particular example, what is f of t? First you have to identify. So that's why I told you, you have to observe this thing very carefully. What is f of t? Now here in this example, as you can understand, if this is the delta function, so whatever is multiplied with the delta function is nothing but your f of t. So your f of t here is actually 3 t to the power 4. 3 t to the power 4, sorry. Okay, this one. And what is the alpha or a in this case? What is the alpha or a? Here, suppose a is equals to 1. Look at this. Delta t minus a. So t minus a means t minus 1. T minus 1 make it equals to 0. So t equals to 1. So t equals to 1. That means a is a or alpha, whatever you say, or alpha, whatever. Sometimes we use a, sometimes we use alpha. So a or alpha is basically 1. So shifting by 1 unit in time axis. Okay, so delta basically exists, its function exists at t equals to 1 value. So now if we just simply apply the property, then it could be reduced to, it is what is the formula? 3 here it was f of a. Please note it, f of a into delta t minus a. So f of a means this is ft. So f of a nothing but 3 t to the power 4 evaluated f of a in a means 1s, evaluated at t equals to 1, this, and this is multiplied with delta t minus 1, t minus a. Here a is 1, so t minus 1. So what is this? This value is basically nothing but t. It's right, 3, nothing but 3, because t is 1. So 3 into delta t minus a, 1. As simple as this. So if you can do it, you will get 2 or 3 marks very easily. Likewise, suppose if we go for the another example, say example number 2. This is 1. This is example number 2. Now, say in this example, the expression that is given is something like this. তোমাদের এত ঢুকতে দেরি হচ্ছে কেন? টাইম অনেকক্ষণ হয়ে গেছে তো, আমি অনেকক্ষণ ওয়েট করার পরে স্টার্ট করলাম। এই মাঝখানে ঢুকলে ইন্টারাপশন হয় বড্ড। f of t delta t minus alpha. Okay, so just a minute. Let me put a value here. Suppose t delta this is the expression given. So just reduce it and tell me what will be the value. Please note here you have to integrate. So that means the at the right hand side, whatever you will write will not be a signal in a signal form. It will be just in value, unlike this case. Okay, so just tell me what will be the value. Just apply the property and tell me. Any one of you.
2, sir.
2, very good. 2. Just 2. The numerical value, nothing else. It is just a value. Please note it. Look at the difference. Here, in the previous example, it was a function or in general a signal of a function of time, that means a signal. Here, it is no connection with the any variable or the time. So it is just a value, just a numerical value. So that is the difference. I think I have already mentioned it. So this is 2. So simple it is. Now, suppose example 3. Another example. Take example 3. And here the expression which is given is t, suppose t square, say t square, then delta prime, please note it is delta prime t minus 3. Evaluate this or reduce this just by applying the formula. Tell me, anyone.
9 delta t minus 3.
9 delta
T minus 3.
t minus 3. Then anything else?
No, sir.
No, this is not right.
minus 6 del t minus 3.
Minus 6.
6. Yes, it will be derivative f of a prime. And del t minus 3.
Del t minus 3. Here del t minus 3. Here also del t minus 3.
Oh, no, it will be integrated. No, wait.
Check it. And
It will be 9 del dash t minus 3 minus 6.
del dash, very good. 9 del dash, del prime t minus 3. The first term will be 9 del prime or del dash t minus 3. Then minus 6 into
Del t minus 3.
del t minus 3. Very good. Del t minus 3. That's all. So this kind of question you can expect in the examination. Okay, so a short expression or a small expression will be given and you have been asked to evaluate this just by exploiting the property of the delta function. That's all. Now, so basically we introduced 2 things. One is how to represent any complex signals in terms of your basic or elementary signal. That means, in other words, we can say we can decompose any complex signal. Given any complex signal, you can decompose it into a sum or actually addition and sum or difference, the same thing actually, of some basic signal. Say in our case, unit step function. Okay, so we represented any complex signal in terms of the unit step function. That skill we have already developed. This is another thing. So we have also become familiar with the different properties of the delta function, its differentiation, what is the meaning of differentiation of delta function, the property associated, that means the sampling and the shifting property is associated with the higher order delta functions, and a little bit example with these small examples, a bit familiar with how to apply those formulas and then how to evaluate the expression and so on. So if we have developed these two skills, then we can incorporate or can apply simultaneously to evaluate a big or a complicated waveform in a following manner. So suppose I'm going to share this slide with you. In the left-hand panel, look at the waveform. Now your task will be, it is a very complicated waveform, as you can understand, in comparison to what we have already done. So here we have to express all this voltage waveform. Suppose it is Vt, it is written or defined, and as a function of time is in second. Please note, unit is given here, so it is in second. So, and it is in voltage. So Vt as a function of t, V as a function of t. So, and that interval is from -1 to +7. Please note carefully, -1 to +7. A typical waveform, complicated waveform is given. Now, you have basically two tasks. So, first task or first part of your assignment or job is, I'm giving you as a home assignment to you. So, you have to do it and come up with the solution. So the first part would be, you have to express this voltage waveform as a sum of unit step functions for this interval. Look at this interval, -1 to +7. Okay, this is the first part of the question, you can say. So you have to basically express this voltage waveform as a sum of unit step functions for this interval given. Now the second part, what you have to do, you have to, using the result of the first part, of course, you have to compute the derivative of this Vt. Whatever the function is given, you have to differentiate it. So you have to compute the derivative, and while computing the derivative, you have to basically apply the result or invoke the result that you got from the first part, as well as you have to apply the properties of delta or higher order delta functions as applicable. Getting the point? So with this, you have to just express it in a reduced form, and not only that, you have to draw the sketch of that resultant waveform. That is, after doing the differentiation, what would be and applying the properties of the delta function properly. So what would be the resultant waveform, or how the resultant waveform would look like? You have to just draw it. So these are the two tasks you have been given. So just do it in your home. And in the next week, coming week, I will check it. Okay, so I will randomly ask you to share your screen, and I will just check there. Okay, now understood?
Yes, sir.
Okay, now with this, let me again go back to the previous screen. Just clear it. Now, so as far as our concept of delta function is concerned, not only the concept of delta function, but other basic or elementary functions as well, like the unit step, unit ramp, and etc. etc. So as far as the continuous time domain, they are related to each other either by differentiation or by integration, as you can understand. So, but likewise, in the discrete domain or in the digital domain, discrete time domain, or in general, you can say the digital domain. In the digital domain also, these elementary signals, like you can represent it like, suppose delta of n. Delta of n, instead of t, it will be n, and n is here the number, and the numbers are strictly to be integer, as you know. Del n, suppose un represent the unit step in the discrete time domain, or in general the digital signal, you can say also. So these, or Rn, the ramp. See, all these are also the basic signals. Okay, these are also the basics or the elementary signal in the in the discrete domain, or in the discrete time domain, better to say. Okay, so these signals are, but the difference is, logic is same, concept is same, but the difference is these signals are very simple to understand as well as to apply, unlike the case of continuous time domain. Because there, suppose you have to differentiate the unit step to get a delta function in the continuous time domain. In the discrete time domain, you don't need to do that. It is a very simple way you can find out the delta function from a unit step function. in a very simple way. How you can do it? Very simple thing. Suppose you have a unit step. How to write a delta n in terms of the unit step? Delta n is nothing but, first of all, what is delta n in discrete time domain? So delta n, suppose this is in numbers are there, this axis, number axis. So we have different values, already AKS had introduced, so I think you are already familiar. So suppose different negative values, suppose -1, here in this direction, you have different minus values. Suppose this is 0, okay, this is 0, this is +1, this point is suppose +2, and so on and so forth. And here this delta function should exist only at n equals to 0, and you don't need to give any arrow or something at the top of this delta or this bar. It is just a bar, and sometimes people give a kind of draw a circle or kind of a point like on the top of this bar, and the value or the magnitude is precisely 1. That is unlike the case of delta function in the continuous time domain. There 1 means actually area. Here 1 means actually just a magnitude, because there is no concept of area here in the discrete time domain, as you can understand. So here 1 indicates actually the value, the magnitude. So you have this bar whose magnitude is 1. That's all. So simple it is. And that is located precisely at n equals to 0. N equals to 0. So no concept of an area or something. So it is much simpler. Just the amplitude is simply 1, and it happens to be at n equals to 0, or located or occurs, whatever language you can use at n equals to 0. Now your next task is how to represent un here. So you can represent un like, suppose you have the same axis, and un could be represented like at n equals to 0, you have a bar whose value or amplitude is 1, which is simply 1. Then at n equals to +1, again you have another bar, which is again 1. At n equals to +2, another bar, which is again 1, and so on. In this way, it will continue up to n equals to +infinity. So it is 0 onwards. And for the -1, -2, and so on, in this side, left-hand side, you have all the value that is 0, precisely equals to 0. So just note the difference. Here, for the discrete time case, discrete time unit step function case, at n equals to 0, the signal has precisely the value of 1, that means it could be defined precisely, okay? But that is not the case in case of continuous time domain unit step function. So here also just if you compare, it is much simpler. No ambiguity, no confusion. Okay, it's a very simple way you can define and represent also. So this kind of so basically different bars having the same amplitude actually continues from n equals to 0 onwards in this direction, in the positive direction. So now the task is to find out this from this unit step. So find out delta n from the unit step. Very simple. Just by looking this two picture, you can immediately say. So it will be just an un minus u of n minus n. So all the mathematical operations that could be done on the signal for the continuous time domain could easily be done on the discrete time domain as well. So that means the shifting in the right-hand side, it's flipping, all kinds of operation, multiplication, and so on and so forth. Okay, flipping at this side, flipping at that side, okay, shifting, you're delaying, advancing, multiplication, etc., etc. So all kinds of operation is equally applicable for the discrete time signals as well. Now, so just look at this expression, how simple, how innocent it is. So just an even you have you have another signal which is u of n minus 1. That means this is shifted by one sample. All these are the kind of samples, because ultimately how you get this discrete time or digital signal, you have to sample, right? So that is why people call it's a sample. Okay, sample. It's automatically come. It's inherent to this term is basically inherent to this kind of discrete time or digital signal. So if you don't do the sampling, you cannot make the continuous time domain to the discrete time domain. So that is why these bars are actually on the sample values. So suppose these are the different sample values, and different samples having the value. All values are 1, exactly equals to 1. Here you have only one sample value which is equals to 1. Now, so if you just shift this signal to the right hand side by one sample, then ultimately you will get this kind of signal, this having the same, all the samples are the same value of the same amplitude. So if you just subtract this from this, so ultimately all the samples from n equals to +1 onwards will be cancelled, and then you will be remain with this only one sample having the value 1 and located at n equals to 0, which is nothing but your delta n. So in this way you can find out delta. So simple. Similarly, in the reverse manner, in the reverse way, you can find out the delta n just by you can find out the un with the help of delta n also. In case of your continuous time domain, you know that to find out the delta t from ut, you have to differentiate, and to find out ut from the delta t, you have to basically integrate. Now here, what you have to do, the differentiation becomes just a difference. As I think in the last class I mentioned, the difference. Look at this, and the integration now will become just a summation. But concept is same. Getting the point? So here, what will be the expression un? My task is to represent un in terms of the delta n. So that means what? Different delta functions are there, different delta n's are there. So you have to just add, simply add. But the point to be noted is that the delta functions are not located at all the delta functions are not all the delta functions are located, but the different values of the n. That means some of the first delta function is located for n equals to 0, the second is for n equals to +1, the third for n equals to +2, and so on and so forth. That means they can be thought of as a shifted version of the original delta function, which by definition is to be located at n equals to 0. Now, so un is nothing but the summation, the sum, the limit of the summation should be from n equals to 0. So 0 to infinity, as you can understand, because the unit step actually located from 0 to infinity, all the samples. So use some other variable, suppose k equals to 0. So 0 to infinity, this will be the limit of the summation, and this delta functions, all the delta functions in general, shifted version. So when k equals to 0, it is a simply del of n, which is located at n equals to 0. When k equals to 1, it will be just delta n minus 1. So delta n minus 1 means delta function, which instead of locating n equals to 0, actually located n equals to +1 at this point. So if I just suppose erase this and draw a delta function at this point, this is nothing but delta n minus 1. Now again, plus delta, when k equals to 2, delta n minus 2. So delta n minus 2 means suppose this function actually shifted, and now it is located, instead of n equals to +1, it is located at n equals to +2. Otherwise, except the location or point or the point of occurrence, all other properties will be retained. That means the shape, its value, everything will be retained. Getting the point? It's just simply shifted or slided in the right hand side by one sample. From this to this, it can jump. It can in between, it cannot reside anywhere, this sample. Okay, so this is up to infinity. If you just sum, you will finally get the un. So that is basically, these two as a whole give you a very powerful information, and ultimately which is the relationship between delta n and un. So the relationship between delta n and un for the discrete time case or the digital signal case is clear. I think the relationship between the delta t and ut for the continuous time case or continuous time domain signals are also clear to you already. So I think you can deal with this kind of signals very well. Now, suppose we have a sequence which looks like this. -2, -1, this is 0, this is 1, this is 2, 3, all should be spaced. Okay, 4, 5, though my drawing is not very good, but I think you can understand. And the signal at 0, we have 0. At 1, I have a bar. I'm having the amplitude 1. At 2, I have another bar having the amplitude 2. Suppose this is 1, this is 2, At 3, I have another bar having the amplitude, suppose 3. Okay, so but at 4, I have 0. At 5, I have 0. At -1, I have 0. At -2, I have 0. So in the screen, or on the screen, this picture is given only, or this sequence is given. That is a graphical representation. You know that signal could be represented in many ways. This is one of the representations or modes of representation. So it is the graphical representation. You can also represent in terms of the sequence as well. I think AK sir have already discussed this thing. So now, if anyone asks you what is the length of this signal, just given this picture, if anyone asks you what is the length of the signal, this is of course a finite length signal, as you can understand. It has a finite length. It is not an infinite length signal. And what will be the length? Can anyone tell me what will be the length of the signal? Quickly.
7.
7. Okay. Anyone else?
3.
3. Okay. Anything? Any other answer? 3 and 7. I got 2 types of answer. Any other kind of answer? No other answer. Only these 2 options are available. Either you have to go with 3 or you have to go with 7. Nothing else. Okay. Actually, the length. Okay, 5. Actually, the length will be 4. Neither 5, nor 7, nor 3. The length will be 4. It ranges from 0 to 3. Okay, 0, 1, 2, 3. That's all. 4. Because the sample at, please note it, this is n axis. This is x of n. Okay, this is x of n. This is x of n. This is n axis. Okay, this is n axis. So for the 0, 0, but at n equals to 0, you have a sample whose value is 0. That means whose magnitude is 0. But that 0 you have to take into account. But one might say that, as already, I think one of you already told me that the length would be 3. Probably he counted these 3 samples which have non-zero value. Am I right? So he counted these 3, and that's why his answer is 3. But these 3 non-zero samples are located for n equals to +1, +2, +3. Now, what about n equals to 0? Please note the significance, because after all, that's not a value. This is not just a sequence or the value. It has some significance. It is after all signal. It is giving you some message, some information. So n equals to 0 represents the present instant, as you know. So what is the value at present? If you don't define anything, then by default it is assumed that it has 0 value. So you have to take into account that present instant. Without taking into account the present instant, you cannot only consider the past or the future. So the present is very important. And this is kind of a pivot, okay, or the reference level, which you cannot ignore. So if one say that the length is 3 because due to these 3 non-zero values located at 1, 2, and 3, but this actually belongs to future values or related to the future values. If you go for with a simple concept, okay, but you have to take care of this 0. That 0 means this 0 represents, please note, n equals to 0 represents the present instant. This is kind of pivot. Probably you have seen this notation, this arrow, upper headed arrow. This indicates the 0 pivot element, which is actually the present or the current instant. This 0, but this 0 here, this 0 indicates the value or the amplitude of the sample. Yes, you may argue that, sir, that means no sample is present. Yes, I agree with you. That is possible. No sample is present. Or it may show up and there is a sample whose value is 0. That is also possible. But basically the same thing. Okay. But still you have to count. Still you have to count. So the length of the signal would be from this to this. Now, the next argument, which may naturally come, sir, why we are not counting these zeros and that zeros? Which is in the left hand side or in the right hand side? Because as you can understand, right hand side, there is no need to count, because after this non-zero value, all the values that is coming are all zeros. So no information is hidden. Similarly, these values, this left in the left hand side, for the negative values of the n, whatever values are, all are 0. So again, no information is hidden over there. So nothing new. So that means this is kind of fuzziness, as you can understand. Kind of fuzziness is reflected to this kind of scenario. But still, you have to understand it very carefully, that to always consider the length. Suppose instead of this, if it so happen that I have a sample here, then you have to count this 0. Please note it carefully. In between, or suppose if it so happens that here also you have another sample, which is non-zero, or which has a non-zero value. So that means then the length of the signal you have to count from this to this. Then what would be the length? The length would be simply this. Here you have 1, 2, 3, 4, 5, 6, 7, 8. Because please note, sometimes people call it 7. The problem is, it is not, they forgot to count this 0. It is not 7 actually, as you can understand. From 0 to 3, here it is, I have written 4. Similarly, 0 to 5 means actually here it is, you have 6, and here you have 2, 8. So basically, you have 8 samples in that case. But we actually intentionally omitted these 2 only to create some sort of confusion, some fuzziness. Getting the point? So in that case, for this, it is a very typical, very smart example people cite sometimes just to confuse the students. So this example clearly tells you or gives some kind of understanding that what to count and what not to count, and why to count and why not to count. So in that case, the length would be 4. Argument could be made in any ways, but ultimately you have to counter that. So that okay. So in this case, how to represent the signals? You can represent the signals either in terms of the delta functions, or you can represent the signals in terms of the unit step function. Both are possible. So if you represent in terms of the delta function, so delta function is suppose xn. So the first delta function gives you 0 value. Delta is 0. So there is no need to write it. There is no need to write it. Please note that though I am telling the length of the signal is 4, but still while representing the signal, I am not writing delta because delta n is 0. I cannot write delta n. Delta n means if I write delta n, what is the meaning of that? The meaning is at n equals to 0, you have a delta a bar whose amplitude is 1, which is not true. So I cannot write delta n. So the first thing I have to write, that is delta n minus 1. One sample shifted version of delta n. The second case, say for the second sample, what should I write? It is 2. So definitely amplitude is 2. So simply multiply by 2. 2 delta n minus 2. The third, 3 delta n minus 3. So simple. This is just a representation in terms of the delta function. Now, similarly, if you have been asked to represent in terms of the unit step function, so how to write it? X of n. How to write it? Just you apply the concept of what you did in case of a continuous time case, or the continuous time level signal. Just to apply the concept here. I want to get a correct answer in this time from you. How to write it in terms of the unit step function? Please proceed. Otherwise, you will not learn.
Sir, u of n minus 1 minus u of n minus 2.
U of n minus 1. Then
Minus u of n minus 2.
minus u of n minus 2. First, to draw
Plus-
u of n. Okay. Continue, please.
Plus u of n minus 2.
Plus again u of n minus 2. So this will cancel each other, no? U of
Sir,
n
I'm
mi-
trying to actually represent each delta function by using that impulse that
Okay. You are trying to represent each delta function by unit step function. Okay, understood. Then you just tell me the final expression. Getting the point? Just final expression. Others? Please attempt it. It is very simple. You have already done it in case of a continuous time domain signal. You represented this type of signals in terms of the unit step function. You have already done it. So apply that concept.
Sir, un minus 1 plus un
Final
minus.
form. You are telling the final form.
Yes, sir.
Okay.
Un minus 1
Okay.
plus un minus 2
Un minus 2
plus sir, one second. Plus un minus 3 minus 3un minus 4
un minus 3. Then
minus 3un minus 4.
3un minus 4. Okay. Have you drawn and cross-checked whether after summing all these 4 components you are getting this? Have you drawn it on your paper? You draw u of n minus 1, then u of n minus 2, then u of n minus 3. So basically what she is trying to project is that the first un minus 1 will give you the sample 1 at n equals to 1. Un minus 2 will add another sample having the value 1 at n equals to 2. So that means it becomes 2. Okay. Then n minus 3 will add another. So that means 1 plus 1 plus 1, 3 actually at n equals to 3. And when you are basically subtracting from n equals to 4, they cancels each other. Now, everyone agree is with this? Is it okay? Is it correct?
Yes, sir.
Correct.
Yes, sir.
Okay. Is there any other way to represent it? Is there any other way to represent it in terms of the unit step? Which should be even simpler. This is okay. Say suppose this is correct. Suppose then alternative.
Sir, n into u into n minus 1 minus. Sir, if I multiply, I mean this line and the slope, and then
Yes.
subtract.
Yes. You are on the right track. Exactly. I got your point. Very good. Actually, first of all, the same concept I'm telling you, no, just apply the concept what you have developed for the continuous time case. So what you did there you first try to identify the length of the signal, the length up to which the signal exists, or the span of the signal. Here it is 4, so that means 0 to 3. So the first you have to draw a function which would look like a get function, just a get function. So here it will be just u of n minus u of n minus 4. Got it? Let's understand this thing. U of n minus U of n minus 4. So what it will give you actually? It will give you basically a get function. It will give you basically a get function which is located from, the function should look like this. 0, 1, 2, 3. 0, 1, 2, 3. That's all having the value 1. So un minus U of n minus 4. So 4 onwards, everything got cancelled. Now, this is called the get function. In a continuous time domain, this signal looks like something like this. Square function or get function like. Okay, so they are basically equivalent, analogous. Fine, this get function. Now what you are doing? So what C is trying to tell, C actually wants to multiply it with the slope of the straight line, which is nothing but your n. So that means if you multiply n means when n is 0, it is 0. When n is 1, it is 1. When 2, it is 2. 3, it is 3. That's all. So if you multiply this with 0, so the first, for n equals to 0, it will become 0. If you multiply this value, n equals to 1, so for n equals to 1, this will become 1. If you multiply this one with n equals to 2, then it will become 2. And if you multiply this with n equals to 3, it becomes 3. And so resultant signal, it is this, and the resultant signal is similar to this. So this is another way to represent. Okay, thank you. So this is the kind of the different ways to represent my xn, or in general any kind of discrete time signal. Now, first let me clear the screen. Now, another sequence actually we very often encounter in our life, and it is a very great significance. That is the exponential sequence, which is in general represented like I alpha to the power n. It's in general represented like a alpha to the power n. That means this sequence, suppose if it starts from n equals to 0, suppose n equals to 0, then the values that we are going to get, the first value will get is suppose a, then for n equals to 1, suppose a alpha, then a alpha square, and so on. Okay. Now suppose if it starts from n equals to minus infinity, then this sequence a alpha to the power n is actually should be started from minus infinity, and then it actually reduces. But in the left hand side also, I can have different values like a alpha to the power minus 1, here a alpha to the power minus 2, and so on. So that means for the first case, it is just a right-sided or right-handed signal, And the second case is a both-handed signal. So you have the values for the past instances, you have the values for the present instant, as well as for the future instance. So in all the directions, you have the values for the positive domain, positive values of the n, negative values of the n. In the first case, you have only the present and the future. So that means only for the positive values of the n. Now, suppose if a alpha to the power n, this function starts from n equals to 0 and tends to infinity. The way to ensure it, how we can ensure that a function a alpha to the power n only starts from 0, n equals to 0, and should tend for infinity, means positive values of the n. It's very simple. You just write a, that means this sequence. How to represent that? A alpha to the power n u n. If you just multiply it, un, it clearly indicates that this is a right-handed signal starting from n equals to 0 and going towards n equals to n plus infinity. Simply multiplying by un, you got this information. So clear, so simple to represent it. But if you, instead of un, if you don't write un, then there will be some ambiguity. But in general, you can say in that case, this is a both-sided signal because nothing is written. Nothing is written. Now, can anyone tell me if I want to represent it in a fully left-handed signal, or in terms of a fully left-handed signal or left-sided signal, then what I should multiply with a alpha to the power n? When I'm trying to represent it in a right-sided signal, as a right-sided signal, I multiply it with the un. Suppose if I want to represent it as a left-sided signal, only as a left-sided signal, then which term I should multiply?
Sir, u of minus n.
U of minus n. Everyone agrees?
Yes, sir.
Okay. Suppose I don't want my signal to be started from n equals to 0. Rather, it should be started from n equals to minus 1. And it should go towards the minus infinity. What is the term that I should multiply?
U of minus n minus 1.
U of minus
Yes,
n
sir.
minus 1. U of minus n minus 1. That means minus n minus 1 is 0. Fine. Then minus n equals to plus 1. So n equals to minus 1. Okay, correct. U of minus n minus 1. Correct. Right. So in this way, you can do any kind of operation. You, according to your choice or requirement, you can start the signal at any point you want, and as well as you can continue up to your requirement. Fine. Okay. Now the concept that comes is the concept of a bounded sequence. Bounded sequence. The question is this signal is bounded? Is this signal bounded? If the question comes, the answer should be that obviously not, because no, actually I should not say like that. Just a minute. Okay. Actually, if the question comes like that, so we can say that basically if that mod of alpha is less than 1, if then it is bounded. Because you know, in general, alpha may be real or complex, may be positive or negative. You don't know because I've just written alpha. You don't know what is the exact form or the value of the alpha. So we have to consider the general case. So mod of alpha should be less than 1. If it is less than 1, then it is bounded. If mod alpha is greater than 1, then this right-sided, this is RSS. In short, people use it RSS, and the left-sided LSS. So this RSS is not bounded. And basically it increases, as you can understand, it increases indefinitely to infinity. Now, suppose if it is not a right-sided signal, then if anyone asks you in general, suppose the sequence only a into alpha to the power n is given, no u of n or u of minus n kind of multiplicative factor is there with, or the signal is there with a alpha to the power n. So in that case, if anyone asks you only a alpha to the power n is given, now the question is whether that will be bounded. Now, so are there some condition which will make this signal bounded or a bounded sequence? The answer will be no. No, of course no, not at all. Because if you just think carefully, that if mod alpha is greater than 1, because either mod alpha will be greater than 1 or less than 1. That's all. Now, if it is greater than 1, so in this case, suppose if it is greater than 1, then what would happen? Your right-sided sequence will be unbounded, the right-sided part. If it is less than 1, then the right side it is bounded. Suppose this right side it is bounded, but the left side is unbounded. But this signal in general has a both side, left side, right side. So either of the side will be unbounded, depending on the value of alpha. Whatever alpha you choose, whatever alpha greater than, less than, doesn't matter. Either one side will be unbounded, either right or left. So in general, you can say no. In general, you can say that it is not a bounded sequence. That means there is no condition for which one can make it bounded for any value of alpha. Okay. So in general, I can say that a alpha to the power n in general is unbounded and increasing magnitude of alpha, irrespective of the magnitude of the alpha. We can say that. Okay. Now, suppose if we extend our discussion a bit further, suppose if we consider another important signal which we encounter again in our practice quite often, and especially in the communication, you will encounter while transmitting different types of information, you will encounter this signal very often, and that is called a sinusoidal signal. That's cosine or sine. So suppose let me write it in some form. Suppose a cos, what should we write? Okay, omega 0 n plus phi. Suppose some form I have written in general. Okay. Now the question is again whether it is bounded. Is it bounded? Whether this signal is bounded? Is this signal is bounded? So what would be the answer? The answer would be actually bounded means, first you have to understand, bounded means is related to is amplitude, not the extent or the length. Here in general, this signal actually extended from the minus infinity. I think I have already told you this before, that in general, any cosine or sinusoidal signal, or means sine or cosine, means sinusoidal signal, actually infinitely extended. That is from minus infinity to plus infinity in general. Okay. So here also, this signal is in general infinitely extended. But the extent is infinity, length is infinity. But the point, as you know, that cos can maximum attain plus 1, then either plus 1 or minus 1. So a multiplied with a, so the maximum value is, if a is finite, so as you know, so then the amplitude is always going to be finite. So that means yes, it is bounded. So the maximum value is a. That's all. Whatever the value a has or a got, the signal will give you the same value, the maximum value a. So yes, it is bounded. In general, it is bounded. Even though the signal extended from minus infinity to plus infinity. So it is bounded. Now, the next obvious question that should come, whether this signal is periodic. First bounded, then periodic. Periodic. Whether this signal is periodic. The answer in this case would be very, very interesting. The answer would be not an unconditional yes. That means, what is the meaning of that? Meaning, you have to, without checking the condition, you cannot say whether this kind of signal is periodic or not. Now, you may wonder, but what I am telling? It is a sinusoidal signal, but still I am telling, without checking the condition, I cannot ensure that whether the signal is periodic or not. It may be periodic, it may not be periodic. Now, the point is, you have to remember here that this is no longer a continuous time domain signal. This is in continuous time domain, all sinusoidal signals, whatever we learned so far, all types of, okay, the conventional, in a conventional way, or whatever we learned or familiar with, are all periodic in nature. So, without checking the condition, we can straightforward say, yes, it is periodic. So from the childhood days, we are basically familiar with dealing with this kind of thing. But this is discrete time. Please note the variable. It is n. This is n, not t. So that means actually it's in sampled version. Probably you can visualize the way we did sampling. So it's kind of some sample. It is basically a sample version of the original continuous time sinusoidal signal. Some kind of sample version. Now, after doing this sampling, whether till it is retain its periodic nature or not, we don't know. We have to cross-check it. Okay, so without checking, without that kind of validation, we cannot ensure that the signal will be periodic. That means, that is why I told you, your answer would be, whenever anyone asks you whether any discrete time signal, sinusoidal signal is periodic or not, don't blindly say it is periodic. Your answer should be, actually, it would be an unconditional, not an unconditional yes. Okay, so you have to check the condition, then only you can say whether it is yes or no. Now, let me elaborate the fact, okay, further. Suppose xn equals to a cos omega 0 n plus phi is to be periodic. Suppose, then suppose if it has to be periodic, then what is the condition that has to be satisfied? The signal has to satisfy. And you know that there must be. Sorry? কেউ কিছু বললে? যে বলছো তার ভয়েসটা ব্রেক করে যাচ্ছে, আমি শুনতে পাচ্ছি না।
Okay, sir. Sir, I have poor connection. That's why my voice is breaking. So
Yes, his voice is breaking. His voice is breaking. I'm not clear. Anyway, so if this has to be your periodic, then obviously you know the condition that x of that would be some quantity capital N, so that x of in general, sorry, n plus capital N should be equals to x of n. You know this condition very well. Okay, now suppose in this, now here forget about this a, forget about this phi, etc. Okay, let's continue with the phi. Okay, let's continue with the phi. Forget about the a. Okay, a doesn't carry any additional significance in this context. So anyway, so cos omega 0 n plus phi, and you have to satisfy this condition. That means there should be some quantity, some number n. Please note here n is a number because after all it is a discrete time case. Now, if you have to satisfy this, then we can write cos at this side omega 0 instead of n, it would be n plus capital N plus suppose phi. If you want, you can write, otherwise you can omit also. It doesn't matter. This cos, this has to be equals to omega 0 n plus phi. This is the condition. And the question is whether this is equal or not. Now, if they has to be equal, if both the sides have to be equal, then obviously this should be true, that omega 0 into capital N should be equals to 2 pi, you know that, into R. Okay, and what is R? R is basically an integer, you know, that is basically the integer multiple of 2 pi, it has to be. So, if you just rewrite this in some different way, I can write it that omega 0 divided by 2 pi would be equals to R by N. R by N. Now, what is R? As I mentioned, R is an integer. And what is N? N should also be an integer. Because after all, all these are the sample values, so the sample instance. So, in number. So it has to be an integer, no other way. So look at this. This is basically ratio of two integers. That means it is called technically, what is the technical name? Rational number.
Rational number.
Exactly, rational number. Okay. So it has to be. Now this is the condition we're imposing. If this ratio omega 0 divided by 2 pi actually reduced to a rational number or gives you a rational number, this ratio, then it is guaranteed that this is a periodic signal. That means then the condition is valid, satisfied. Otherwise not. But this is always not guaranteed. So without checking, you cannot say, because R divided by N has to be an integer. has to be a rational number, ratio of two integers. And now please note, look at the left hand side, omega 0 by 2 pi. Now omega 0 by 2 pi, what is omega 0? Omega 0 is this frequency. And this is for the digital signal, so that means it's the digital frequency, omega 0. Omega 0 by 2 pi. Now suppose, let's take a simple example, just to elaborate this fact, or to substantiate this fact. Suppose cos 3n, this signal is given. If it is given like cos 3t, then we can easily say it is a continuous time domain signal and it is periodic, no doubt, without checking anything. But here, the problem is, it is n instead of t. The variable is n, the number. Now, here, what is omega 0? So omega 0 is basically 3. Now, if you take this ratio, that means apply this condition, omega 0 means 3 by 2 pi. So 3 by 2 pi, as you can understand, is not a rational number because pi is not a rational number after all. Okay, so it is basically an infinite number of digits. So it is not a rational number, pi itself. So as pi is not a rational number, so it is very difficult in many occasions to get this kind of rational number, or the ratio will become a rational number as a whole. Only if some pi is associated, then there is a chance that the pi gets cancelled and the number could be a ratio of 2 integers. Could be. There is a possibility. Okay. So anyway, so the bottom line that we want to draw here is that we in analog or in a continuous time domain case, sinusoidal signal, we can say easily, as far as the signals we have dealt with so far, the types of sinusoids we dealt with so far. So just seeing the function sine of something within the bracket, we can say it's a periodic. Okay. But if it is the case of digital signal, we cannot blindly say that. We have to, it may not be periodic. We have to check this condition. If this condition is satisfied, then we can say it is periodic. If not, then it is not periodic. That's all. Simple. Okay. Now, suppose if we want to go a little more interpretation with this signal A cos omega n, omega naught or omega whatever, same thing, omega n plus phi. This. Okay. Now, just if you imagine how we got or obtained such signal. Suppose the analog signal, what is the analog signal? Actually, its analog counterpart was originally supposed A cos t plus phi, suppose. This was the original analog cosine signal. Okay. Here the variable was t, and this is small omega, this is capital omega. The capital omega is the frequency, the angular frequency, capital omega t plus phi. This was the form of its analog counterpart. Now, after sampling is kind of switching, as you know. So this kind of symbol people use. So after this, what we got actually, if you people were present, or those who were present in my first two classes, they know very well how to represent it. So A cos, so just after sampling, what we do, the argument, I'm writing the argument here, okay, after cos. So here I can write this capital omega, then t, instead of t, it actually should become n into capital T, and you know what is that capital T? Capital T is basically the sampling interval or sampling period. So while sampling action or operation is done, so sometimes people write here the T, okay, at the bottom or at the top. That indicates, so it is the speed or rate. That means after every t second you did your sampling. So anyway, so after that you can represent your sample version as this capital omega n t plus this phi, suppose. Okay. Now after doing the eddy conversion, and all the stuffs, so what you finally got is A cos omega n plus phi. Fine. So this signal is actually related to the original continuous time domain signal, as I've already mentioned. So if you now want to relate these two means the frequencies of these two signals. One was the original signal in the continuous time domain, whose frequency was capital omega, and another is a sampled version, or after sampling doing some conversion, the version we got is a cos small omega n plus phi. Okay, now how these two are related actually? How these two are related? These two are related like if you follow the intermediate step, okay, in this procedure. So what we can write is actually this omega is nothing but this capital omega into t, if you just relate these two expression. So the small omega could be written as, just look at this, capital omega into t. Fine. Now what is t? T could be written, it is capital omega, suppose, as 1 by fs. F is the sampling frequency. The reciprocal of sampling period is the sampling frequency, as you know, sampling frequency fs. Now this capital omega is actually in the unit of this is, you know, radian per second. Fine. Now again this can be written, this capital omega can be written 2 pi small f, as you know, the cycles per second, that means the hertz. So 2 pi f divided by fs. Getting the point? 2 pi f divided by fs. Now look at this expression very carefully. This is actually equals to your digital frequency, omega, small omega. Small omega represents your digital frequency. So small omega is nothing but your 2 pi small f divided by capital small fs. Small fs indicates the sampling frequency. Small f indicates the cycle per second or hertz of your original continuous time domain signal frequency. Okay, now this is basically ratio of same types of quantity. Now 2 pi is just a number, so f and fs are the same unit, so unitless. So that means the ratio of same kind of parameter, variables. So your unit, you can omit the unit, so become unitless, and it would be simply this omega is basically simply a unitless or dimensionless parameter. Now people sometimes also write this as, instead of going to the cycle frequency, people prefer to write it in terms of the angular frequencies, ratio of the two angular frequencies, same thing, 2 pi, then it is capital omega divided, instead of fs, it is omega, same thing. Okay, so giving the same information. Anyway, the bottom line is basically, if you notice this carefully, just it is this omega, capital omega is radian per second, but small omega actually has lost its unit, because after all this is the dimensional ratio of the same kind of parameters. Okay, so it is actually unitless or dimensionless. Now how one should express the omega then, if it is in dimensionless? The expression of omega is simply in terms of the radians. Please note, it is just in terms of the radian, not radian per second. Now it is, after all, omega is after all an angle, na? So radian is not a unit, as you know, because after all from this your coordinate geometry, you already know that your angle is basically the ratio of arc by radius. So it is basically, radius actually indicates the angle. That's all. So S equals to arc theta, you already know that. So from that you can say it is just an indication that it is an angle. This is not a unit. Please note the difference. So actually in the analog or in the continuous time domain, the signal has a frequency which has a unit, or the frequency of the signal has a unit, but its digital counterpart doesn't have any unit. It is after all a dimensionless quantity. And not only that, sometimes people also call it as a normalized frequency. It is dimensionless, there's no doubt. So the digital frequencies actually expressed in radians, not radian per second. Okay, radian per second is used to express the analog frequency. A digital frequency is small omega, is, as you know, as you understand, it's a dimensionless. So only to indicate that it is after an angle, people associate the radian term with it. That's all. And sometimes people call it a normalized frequency, because after all, as if from this expression you can see, as if this frequency, this term 2 pi f is being normalized with respect to fs. Okay, or this 2 pi capital omega is being normalized with respect to the capital omega is kind of. So it is kind of normalized also. So anyway, so in our digital signal processing, or while people process this kind of signals in the digital domain, okay, so there is a limit from this. The corollary is that, so there is a limit. The limit is that we cannot go beyond half the sampling frequencies. Otherwise, we will be facing some distortion. And I have already shown you in, I think in my second class, I have shown you the how the distortion could be made, or could happen if you try to basically break the condition, or don't obey the condition. Then what may happen? What is the consequence that may happen? I have already shown you in one of my slides. So this is actually the limitations. Now, so what is the maximum? Then what is the maximum frequency, W max, that we can attain just by looking at this formula? So it is basically 2 pi, as you know, 2 pi f by fs. Now, as I've already mentioned, in the digital signal cases, we cannot go beyond half the sampling frequency. Beyond half the sampling frequency, that means f would be most fs by 2. So fs by 2, as per Nyquist criteria, you know that fs by 2, and this is divided by fs. So fs cancels, 2 cancels. So ultimately, you will remain with pi. So the maximum value that you can attain in the digital case, digital signal case, is a pi. And the maximum digital frequency is a pi, which you can attain. You cannot go beyond pi. You cannot go. So it becomes limited. Please note it carefully. It's extremely important information I'm sharing with you. So in digital, in analog domain, we can go for any frequency. Okay, any frequency, any value you can achieve. But in digital, this what actually imposing the limit? Actually imposing the limit is this fs, the sampling frequency, the sampling rate. So that's why I have mentioned we cannot go beyond half the sampling frequency as per the Nyquist criteria. Then there will be distortion. If you don't follow this, if you don't obey this condition, then there will be severe distortion, and you cannot recover your original signal. The pictures I shared with you. So this actually results in determining the maximum frequency attainable, which is nothing but the pi. Now, so the range of normalized frequency, if I write, this could be written as like 0 omega ranges from 0 to pi. And you know that for a real signal, the sine, cosine, etc. So whatever positive frequency we have the negative part also. And for the real signal, we have basically two parts. That comes from the Euler's relation, you know. So the negative as well as positive. We will also discuss these things elaborately in future. So anyway, it has basically two sides, two spectra, one for the positive half and the other for the negative half. That is the positive values of the frequency, negative values of the frequency. So whatever positive frequencies that exist, there must the negative counterpart should also exist. So basically, so both the directions, okay, the spectrums exist. Now that means this relation can be written like that minus pi omega should ranges from minus pi to plus pi, or in general 0 to 2 pi. Same thing, the difference is 2 pi. So here also sometimes people prefer to write it like this. Okay, so just to indicate that for the real signal, whatever positive frequencies are there, the negative frequencies are also there. So both exist in the spectrum. So that is why you have to counter, because it is basically giving you the basic information, that 0 to pi. But if you consider the whole spectrum, both for the positive side as well as for the negative side, so that means here whatever positive values exist, the same negative values are also exist. So that is why the range becomes minus pi to plus pi, or in general 0 to 2 pi. Okay, this is just for the real signal. Anyway, but in general, if anyone asks you, you can just, this answer is sufficient, that pi is a maximum. And this range is actually called, the baseband. This very, very important name. The technical name of this is baseband, or sometimes people call it the band of vision also. Okay, baseband or band of vision, or that is the window. So that is basically the window. So window ranges from 0 to 2 pi. We actually look into this window. We don't need to bother what is outside. Don't look at outside the window. So our vision is restricted within this limit 0 to 2 pi. Whenever we will deal with any kind of digital signal, we have to look within this range. Specifically, if the signal is real. If the signal is not real, then only 0 to pi is sufficient. Getting the point? So anyway, I'm talking in general. So if you can restrict your vision within that range, in that range, then it is sufficient. It is sufficient. You don't need to look outside that. Don't need to look outside that. But in general, I should write not 0 to 2 pi. Actually, I should write 0 to pi. Okay, 0 to pi. 0 to pi should be the range in general. So now this is, so for what our attention or our focus is only within this range, and this is called the length of the window, or window length. These terms you should be familiar very much. You should be familiar with this term, this window length, okay, window, this kind of terms you should be familiar with. So while dealing with any kind of digital signals, and this is actually an advantage, please note it carefully. This is actually an advantage, because we can say that we are fortunate enough that we have to deal with a very limited range, isn't it? We have to only bother what is there within this range. Whatever is there outside this range, we hardly bother, because after all, it is just a repetition. So that is why dealing with the digital signals are very easy in comparison to the dealing with the analog signals or continuous time domain signals. Okay, because there the range, there is no limit. In general, it is basically plus infinity to minus infinity. In general, any values may be possible, could be possible. So that is why dealing with the continuous time domain signals are very difficult, because the spectrum is actually unlimited. In general, I'm talking. But here it is very easy, because it becomes limited. So unlimited to limited. So this is the conversion. Unlimited to limited. With this process, we basically restrict all the information from an unlimited situation to a limited situation. So nice thing. So nice. So again, your whole task become easy. Your life become easy. All sorts of complications actually get removed. So that is why this is the advantage, the hidden advantage of discretization. And that is why today's world is so powerful as far as the digitization is concerned. Okay. Now, some of the operations that we do with the digital signals, I think already Ekesar has introduced, but still I'm just mentioning here because it is required for for developing some future concept. It is required for me, so that is why I'm sharing with you. So you already, so I think you know that the operations that we very often do with the digital sequences or digital signals is the multiplication. Okay, multiplication. Now, what is multiplication? Suppose you have an XN sequence. This sequence is multiplied with another sequence, suppose YN. These are the two sequences, and producing another sequence that is WN, or giving another sequence that is WN. Now, it means that the corresponding samples are actually multiplied. That means corresponding sample means, suppose for XN, you have different sample values located at different values of N. Like for the YN, different sample values located for the different values of the corresponding samples are multiplied means, I think you got the meaning. That is, for suppose N equals to 0. Suppose for N equals to 0, you have X of 0 as well as suppose you have Y of 0. Then only X of 0 will be multiplied by X, Y of 0. Again, suppose for N of 1, suppose I have X of 1, and again for N of 1, I have suppose Y of 1. So then only X of 1 will be multiplied by the Y of 1. That means the corresponding samples will be multiplied. Fine. That means in general, the ith sample for N equals to I, X, will be multiplied by the ith sample of Y. Like that. And ultimately that will produce what is called the WN. So it is simply Xn into Yn equals to Wn. Simply. Like simple multiplication of two signals or two sequences in general. Now, if you don't have any non-zero value while multiplying, the corresponding samples are being multiplied. So while multiplying, if you don't have any particular value, means a non-zero value of that particular sample, so you just put a 0 there. It is called the plugging the value which is 0. So if there is no sample, or if it is 0, then it is okay. But if there is no sample, so that means you can put the 0 value. This is called the 0 padding. Okay. So 0 padding or 0 adding. Now sometimes it may so happen that these two sequences are not of same length. Suppose the first sequence have started from N equals to 0 and continued up to N equals to suppose 10. Suppose the second sequence started from N equals to -3 and continued up to N equals to 1. Then what do we do? Because if you consider the sequence by sample by sample, okay, the corresponding in all the cases you are not getting the corresponding samples having the non-zero values. Then what people do? People actually, to make the length of the two signals same, what they do, they basically add or pad zeros. That is called the zero adding or zero padding. A very popular question. People ask, what do you mean by the zero adding or padding? So such that the total length of the signal while multiplying sample by samples, that means better to say the corresponding samples should be same. The length of the signal should be same while multiplying the corresponding sample. There should not be any ambiguity or confusion. Wherever there is no sample, you just plug in 0 value. That means it is called a zero padding, as if you are padding zeros. Okay, adding zeros. Either of the term you can use, any of the terms. So this operation is very popular. You will encounter this kind of operation even in your laboratory. Whenever you will do it in, I think in the 5th or 6th semesters. Okay, so this is the objective of this kind of operation is only to make the length of the two signals equal. That is the thing. Anyway, the box by which we represent this operation, this is called the pictorial representation of the operation. This is just a mathematical representation or operational representation. The operation what we are talking about. Suppose if we want to represent a system, suppose we want to represent a multiplier system. So how will we represent? So this is called the pictorial representation. Suppose we have two signals. This is Xn. This is Yn. Getting multiplied and giving Wn. So this is a very simple way. This basically this circle or this circular shaped region within which we have this cross. This cross indicates the multiplication operation. So one arrow indicates that this signal is coming. This is kind of a box where this operation is taking place. So this xn is coming from this direction, suppose yn is coming from this. The arrow is very important, that indicates they are going and moving inside the box, okay, or which is actually in our case the multiplier, within the multiplier. So these are the inputs kind of for this system, and it's getting multiplied, and which is actually coming out of this box of the multiplier is that this arrow indicates that is coming out. Again, that is important. So these two are going in and they're coming out, and coming out, what is coming out? The resultant signal, which is nothing but the product of these two, which is again a signal. But please note, this is signal, this is signal, this is also signal. These three are signals actually. So multiplication, and actually what is multiplication? From the very childhood days, we learn that multiplication is nothing but a repeated addition. Multiplication is basically what is repeated addition. So this operation is actually nothing but a non-linear operation. Non-linear operation. Please note it carefully. Multiplication of a signal by another signal is a non-linear operation. And non-linear operation in this, as far as the scope of the within this course is concerned, we will hardly introduce or deal with this kind of non-linear operation. That means this kind of multiplication, unless required. Okay, so in most of the cases, people try to avoid this because after all, this is a non-linear thing, and non-linear thing will be dealt with a special care and a special method, which is beyond the scope of this course. So that's why I mentioned. But you should have an understanding that this is a non-linear operation, and why it is non-linear, that we will also introduce, or there is some mathematical proof. With that you can understand that why it is non-linear, because it violates the property of linearity after all. So which we will introduce later on. So anyway, so unless at very few occasions, very few instances, we resort to this kind of multiplications, this non-linear operation, if there is no other alternative. If we have to, then we have to. There is no other alternative. But we'll try to avoid. Okay, multiplication. Then comes what is called the second operation, addition or subtraction. So in short, I'm saying A or S, addition or subtraction. So it's the sum and difference, same kind of thing. So here the representation is again the resultant signal Wn is basically xn plus or minus either sum or difference yn. Simple representation. This is the mathematical representation or functional representation, and obviously it's equivalent because these two representations are equivalent. Please note it carefully. This is there. Here also we'll use the block. These are different meanings. Different names. This kind of representation has. Sometimes people call it the block diagram representation. Sometimes people call it the your pictorial representation. Okay. Sometimes people call it the data flow diagram. Data flow means or signal flow diagram, signal or data flow, because after all the arrow actually indicating the flow of the signal of the data. Okay. So different names it actually has got. Anyway, so but these two are equivalent. So here also look at this arrow xn. You are feeding to the system. This sign indicates the summation. Okay. This is yn. Ultimately, we are getting, or what is coming out, the wn, the result output signal. Now, when we do the addition, there is no need to associate any kind of sign, plus or minus something. By default, if this is written or this is given, you can assume that xn and yn are being added. That means here also, please note, the addition or subtraction will be done sample by sample. That means corresponding samples will be added or subtracted. Again, the corresponding word is very important. The corresponding samples are added. That means the x of 0 will only be added with the y of 0, or y of 0 will be subtracted from the x of 0. It is not that the y of 0 will be subtracted from the x of 1. No. Then this statement, the corresponding samples are added or subtracted, will not be true. But as far as the philosophy or the principle of operation is concerned, here, like the previous case, that means the multiplication, the corresponding samples should be added or subtracted. Here people do the mistake actually. So again, if you don't have the samples, you have to again pad or add zeros to just to make the thing uniform or simple looking actually, or convenient for the operation. Now the point is what I'm trying to mention, that if no sign is associated, that is by default you can say it's a plus of your addition operation. Okay, it is simply addition operation. But if to indicate that the same box or same block is actually doing subtraction operation, we associate a negative sign. So this indicates xn, you are subtracting yn from xn. Now if you use negative sign here, then it indicates you are subtracting xn from yn. Okay, so that negative sign indicates actually that which sample or which signal in general or as a whole is actually subtracted from the other. Okay, now just one point you should remember, that generally means in a computer or the microprocessor, actually whenever you will learn the microprocessor and the computer architecture, these things will become very much clear to you. But still in this context I'm mentioning, because I have to mention, so I'm just mentioning, just remember it, and then whenever you will learn all these things in details, you will understand. Even in the next semester, I think next to next semester in the digital electronics, there also you will be exposed to these things. So the point is that in microprocessors or in general in computer, what we do basically, the plus, this minus sign is actually not used as a multiplier. So -1 is not something like a multiply. It is simply changing of sign bit in the binary number, because after all these are the digital signal. So whenever you are representing at the back end, so you have to represent everything in terms of the binary numbers. So this minus, whenever I'm telling you this minus sign, the subtraction, all this, so basically that minus sign is indicating the change of the sign bit. That's all, the sign bit. In conventionally, people use the MSB as a sign bit conventionally, but there may be some alternative algorithms may be possible. But anyway, just to remember this point, so whenever these things will come, you can learn in details. Anyway, so this is all about the addition and subtraction. Next, what comes is your third operation, which is very simple, which is again multiplication, but that multiplication is by a scalar number, just by number. This is not a multiplication of a signal by another signal, unlike the first case. Okay, so the block diagram representation is something like that, something like this. Xn multiplied with, suppose there is a number alpha, okay, and output you are getting, what comes out in alpha xn, or sometimes people represent it like this, xn arrow, here they write the multiplicative factor and then alpha xn, like this. Here also, either this or that. So if we wish to multiply alpha and by xn by alpha, any number, alpha may be any number, any scalar number. Okay, so this either this or that, this any kind of symbolic representation you can use, or okay, the graphical representation, the block diagram representation you can use. So it is just a simple scalar multiplication. Please note, this is not a multiplication of the two signals or the two sequences. And that means it is not a nonlinear operation. The multiplication of the two signals or the two sequences are actually the nonlinear operation. But here it is multiplying a number. That means you have some sequence. You are basically multiplying the amplitude of all the sequences of that particular signal by a particular number. That's all. So all will be equally multiplied. Equally multiplied. Okay. That is why it is not inherently. You can understand the inherent property is that it is linear, not non-linear. Now, the fourth operation is also important, and you also know that is called the time reversal. Time reversal, you know that suppose you have xn, if you reverse it, it will become x of minus n. So just you are basically flipping about the y-axis. So the sense got reversed, and this is kind of flip over. And so what is there in the right hand side will go to the left hand side, and what is there in the left hand side will come to the right hand side. So like you already know that un becomes u of minus n. So un starts from 0 and continues up to plus infinity. U of minus n starts from 0, continues up to negative infinity. So it is just a flipping operation. So that is also very much important. Now in this context, I am suppose we have a signal which does not start at n equals to 0. Okay, does not start at n equals to 0, but start as n equals to minus 1. And it is that means that all the ones in the left hand side, as you have already mentioned, one of you already mentioned just a few minutes earlier, that u of n minus 1. So that signal I am interested with, u of minus n minus 1. This signal. Fine. So here everything started from n equals to minus 1, not from n equals to 0, and continues up to n equals to minus infinity. Fine. So now if we try to develop a DC value, that means if we try to develop a sequence rather starting from minus infinity up to plus infinity, and all having the value exactly equals to 1, how to represent it in terms of this? The representation may be something like, suppose u of n plus u of, this signal has a very special significance, that's why I'm mentioning here, minus n minus 1. Please note, if you do this operation, you have un plus u of n minus n minus 1. So what it actually indicates, it indicates an infinitely extended sequence. It's kind of a DC value, no? Then minus infinity to plus infinity extended. For all the values of n, you have equal valued sample, and the value is exactly equals to 1. So all the n has a sample which is 1, or whose value is 1. So that means mathematically I can write it exactly equals to 1 for all values of n. So simple. That is why I mentioned this has a special significance, and because this actually contributes in making your DC value. Okay, DC value. Now if suppose by mistake, instead of adding this, you have done this operation, suppose by mistake, un plus u of minus n. If you add these two, what will be the signal? How the signal would look like? Can anyone tell me? Un plus u of minus n.
So 2 for n equal to 0, and
Exactly.
for the rest 1.
For the rest 1. So how to represent mathematically? You are absolutely correct. 2 for n equals to 0, and rest of the values are 1. So how to represent mathematically? You can represent in many ways actually. So you can represent like this: 2 for n equals to 0, okay, and 1 for rest or for other values of n, like that. But the simple way I'm trying to write 1 plus, look at this representation, it's a very fine representation, del n for all values of n. Is it okay? This del n exists only for n equals to 0. So it will show its existence for n equals to 0. That means only for n equals to 0, you will get a 2. Because for other values of n, del n would not exist. And then you will only get 1. So it's a very nice way to represent this thing. Un plus u of minus n is 1 plus delta n. Again, this operation is also required in many cases. You will encounter all these things you will encounter in future. So remember, these are the small things I'm basically sharing with you. So it is a great significance and connection with your future courses. So remember these things. Okay. Now, next operation, what we will do is delay. I've already introduced it. So now here I will mainly focus on the block diagram representation. So how to represent a delay in your system. So the representation could be in the form of a block within which you have to write z, suppose minus to the power minus 1. Okay, z to the power minus 1. And here you are feeding this box or this unit with a signal xn, and look at the direction of arrow. I'm basically stressing this point again and again, and at the output, what you are getting is nothing but a one sample delayed version of this xn, which is represented like x of n minus 1, xn x of n minus 1. Okay, now this representation is basically a very special representation because a symbol z is used. Now this will be discussed later by AK sir, while we will introduce the Z transform. This is basically related to the frequency domain representation. In the frequency domain, what happens? Z is a transformation. So tool, okay, which is basically applicable for the discrete time domain, signals and system. So what Laplace transform does for the continuous time domain, the same thing is done for the discrete Z in the discrete time domain, or the Z transform by the discrete time domain. So that is why the conventional way to represent it in terms of this Z, this symbol indicates that it is a Z transformation. So some kind of operation, that is the frequency conversion, transformation operation is being done within this block. So whenever you are feeding any signal xn to this block, so what it is doing, it is basically kind of internally it is happening. It is kind of converting it first to the frequency domain and doing the operation there, and then again it's on the inverse transform. Okay, inverse, after doing the inverse transform, it is giving you back the signal in the domain it was previous, the original. Okay, n minus 1. Fine. Now that Z has a special significance because it relates to the Z transformation, and this is the convention people use conventionally by this. So that is why we have to use this symbol. Now please note, try to relate minus 1. This inverse actually indicates that's delay by one sample. Okay, now suppose instead of minus 1, if we write minus 2, then probably you can already have understood that then it will be delayed by 2 samples. If instead of minus 1, if anyone write plus 1, this will indicate that this sample is advanced by one sample. Signal is advanced by one sample. That means x of n plus 1 will be the output, like this. So this is in the power of the Z, whatever we are writing, that is actually indicating the amount of delay or advancement. Okay, in general. So but now suppose in terms of hardware, what do you mean by the delay? Suppose you are implementing this system and where in hardware, think from the perspective of hardware. Now what do means in one sample delay? It is actually in terms of hardware, is when you are implementing this kind of operation, it is basically there will be some block, some memory, which will store it for some time, and then it will give you. So it is basically one sample delay. So in terms of software also, you can represent the same thing. You can represent the same thing. There also you can implement the memory, and that memory where you can store it and then retrieve it or bring it back to the immediate next sample. So the storing of the past sample and bringing it to the present instant is something like this. This operation resembles this operation. So it is just that kind of delay. So this procedure here, as I mentioned, this symbol has a special significance. But in general, it will always not be -1. Depending on the number of delay you want or advancement you want, you can use. But I already mentioned I think in the last class that there is no electrical system. But in electrical engineering, actually there is no system for which it is possible to make some kind of advancement. So that means some incident or something scheduled to be happen at a particular instant, and is happening before that or prior to that. That means it's kind of a prediction. That means you can predict what is going to happen now. You can predict before. It is not possible for any electrical system or any hardware. It is not possible. So as far as the hardwares are concerned, or the electrical systems are concerned in general, it is not possible to do any kind of advancement. But advancement implies prediction. At present means at present. So what will happen at present, I cannot say before the appointed hours will come. I cannot say. So if I can say, then it is kind of prediction, okay, which is not possible till date. Now that is why this advancement operation is strictly restricted within the mathematical terms. Physical significance, as such, you can say there is no as such physical significance. Again, as far as hardwares are concerned. But anyway, in general, you have to understand that mathematically you can write it. If you want to advance the signal, you have to write here plus. So by one sample means +1, by two samples means +2, and so on. Okay. Now another convention, again, that is also a convention and usual practice people make, we will also follow that, is that suppose we want to give a signal n amount of delay. We want to give an n amount of delay, and the resultant signal should be x of n minus n. I have this xn. After giving n number of delays, I want to get this x of n minus n, n minus capital N. Right? Now, how to represent in terms of the blocks or block diagram representation? So what your answer would be that, okay sir, is in place of 1, I would write capital N. Yes, you are correct. Technically you are correct. I'm not saying you are wrong. But again, this is the convention, and this practice we will follow. We will basically, this is a practice people have been making from the very first day. So we will also follow the same thing. So, and we should be very much disciplined in this particular approach, that we will not write it like nz to the power minus n. Even though mathematically it is correct, but we will not write, because when we will implement this in terms of the hardware, it is not possible to do the operation with a single block. With a single block. What I'm trying to mean is that suppose we have xn. First you have to feed it to a system which can provide only one sample delay for you. Then whatever delayed version you got, again you have to feed it to another system which again will give you another one sample delay. In this fashion, you need, suppose if this is the first block or first delay element, this is suppose the second delay element. In this way, you require nth number of delay element which every delay element in its turn giving you one sample delay, and as a result of this cascading or this series connection, ultimately or the output after this n passing this signal through these n numbers of delay elements. Individually they are the unit delay elements. In hardware, actually these things are implemented exactly like this. It is not possible a one delay element which will give you the n sample delays in general. It's not possible. So you have to basically, while doing the mathematics also, we will particularly follow this discipline. Getting the point? We can, instead of writing mathematically we can directly write, but we will not do it. We will not do it because as far as the implementation is concerned, this is not possible. So that is why we have to follow this discipline. Okay, so then only we will get n minus capital N. This thing. Fine. Okay. আচ্ছা, তোমাদের কি এরপরে কোনো ক্লাস আছে? হ্যালো,
হ্যাঁ স্যার, এসপি স্যার বলছিলেন যে ক্লাস নেবে, জানি না এখন।
এসপি স্যার কটা থেকে?
স্যার স্যার বলছিলেন 3টে থেকে নেবেন, কিন্তু 3টে থেকে তো হয়নি, ওই জন্য আমি জানি না।
3টে থেকে।
হ্যাঁ হ্যাঁ
তো স্যার এখনো কিছু ইন্টিমেট করেননি তো?
না না।
ঠিক আছে, তাহলে আমি একটু কন্টিনিউ করছি। যদি ইন্টিমেট করে বা কোনো মেল আসে আমাকে একটু বলো তোমরা, ঠিক আছে? আমি আরেকটু কন্টিনিউ করছি তাহলে। ওকে, আচ্ছা, তাহলে উইথ দিস বেসিক তাহলে আমরা একটা বেসিক কনসেপ্ট বা আন্ডারস্ট্যান্ডিং ডেভেলপ করলাম, যে মোটামুটি হাউ টু রিপ্রেজেন্ট ডিফারেন্ট অপারেশন উইথ দ্য ব্লক, okay, or people call it the block diagram representation of different operations. The small elements individually, we try to develop some concept on that individually. So what is an multiplier, what is adder or subtractor, what is the scalar multiplier, what is the flipping operation, delay or enhancement, etc. This kind of small, all these operations are very important in their turn. They're very powerful, very important, very significant. But as a whole, suppose if we want to describe a big system or a very complicated system, there it may so happen that different this kind of blocks or the elements you have to incorporate to implement that big system or the big complicated system. Now then how to do it? So a simple example I can cite before you. Suppose a digital system, suppose first let me write a digital system which suppose, I think I have a slide on that, just a minute. Yes, I have a slide on that. Yes, look at this slide. Can you see this slide? Okay.
Yes.
Look at this system. Acha. This system we have, this is basically in general a digital system, a typical digital system that handles some digital signals and operates, do some kind of operation on that, and at the output you are and giving some signal again in the digital form. Okay, so all are digital. There is no analog here. Anywhere, no analog. Now, it's a very simple example, but the system here, as you can understand, that different blocks, individual blocks or components have been introduced. So as a whole, it is basically making a bigger system. Now, here we have done two types of representation, or we have represented the system in a two different ways. Basically, they're equivalent. One is in a mathematical form, look at this, or functional form, as you know already, and another is the block diagram representation, okay, or in general the symbolic representation actually. Now, or data flow or signal flow representation. Okay, so they are basically equivalent. Now the point is, they are giving you the same information. Now if you just follow this carefully, look at this, except this is the input you are feeding at this point. Now at this point, actually this signal splits and following two different paths. One path basically connected look at the arrow, is basically connected through a Z inverse block, means 1 unit delay element block, and then it is being passed through a block which gives or multiplies by the signal, the delayed version of this signal by B1, and then again it is added. It is added here because no sign is associated, so that means it is added with this xn, which is actually following another path and getting multiplied. Again, it's scalar multiplication by B0 and getting added with this. So that means here at this adder is getting, as a one input, it is getting xn directly multiplied by B0, and at other input terminal, it is getting the one sample delayed version of the xn multiplied by B1. Is it okay up to this point? Now this adder is producing the, after addition, is producing the output. This output is being fed to another adder, input of the another adder, whose another input terminal, the other input terminal is fed with the output which is delayed by one sample and multiplied by D1. Okay, now as a whole, the second adder, this version, and this version, when these two are getting added, finally this giving you the yn. So from here also, if you see that at one point you are getting yn directly, what comes directly from the adder, you are getting the yn, that is the output for any nth instant, you are getting it. And another point, you're basically extracting the same yn and passing through a unit sample delay. That means again, you are delaying it actually and multiplying it by a D1 scalar multiplying, and it is being fed to the input of the second adder. So basically here you have two adders, two unit delay elements, one in the input side or associated with the input, another associated with the output, and 1, 2, 3, three scalar multipliers. Okay, so this is just an operation, a typical operation I'm trying to represent here with this block diagram or this signal flow graph. Okay, now the same thing has been captured or represented by this functional or mathematical representation, this representation. Now for the second representation tells you, look at this yn, the output, which is equals to what I have already mentioned you. This is written mathematically. Yn equals to, this is b0 into xn. As I mentioned, this adder, what it is doing, it is taking xn directly multiplied with the b0. So b0 xn plus another version of xn is coming following this path, so getting delayed, one sample delayed because z to the power minus 1, please note it. So x of n minus 1, again this version after being delayed by one sample multiplied by b1, so it is multiplied and fed to the input of another input terminal of the adder. So these two up to this, it's okay. Okay, giving me the full information up to this. Then this point onward, another thing, this adder is actually giving the output. So yn is basically the output of this adder, whose two inputs terminals, what kind of signals are taking? First signal, it is taking this part. Second, it is taking, again it is plus, which is a delayed version of the output, this being multiplied with the d1, so d1 y of n minus 1. So as a whole, you are getting the y of n. So simple. So that means you can put different values of n. Suppose when y of n equals to 0, just put it n equals to 0. If n equals to 0 means suppose the present instant. So at present, suppose when you first started, when you first learn with the system. So when n equals to 0, n equals to 0 means put x equals to 0. Find x equals to 0. What is that? X of minus 1. Here, y of minus 1. Now, if nothing is mentioned about x of minus 1 or y of minus 1 like that, that means there is no initial condition like this. In a circuit theory, probably you have already learned that what is the initial condition. That means there is no storing element. Okay, the system was relaxed initially. So that means before you apply input, you are not getting anything, any output kind of thing. So yn is simply b0 xn, as simple as this, because nothing is being stored, so you are not getting anything. So as if you are getting 0, 0 everywhere. So whatever xn you are feeding, this is getting multiplied and directly following this path and coming here directly. So yn is equals to b0 xn. Now, if you put n equals to 1, so what would happen? N equals to 1 means y of 1 will give you b naught x of 1. Fine. The next instant, the next sample, better to say. And here it will be b1 of x 0. Input n equals to 1, so 1 minus 1, 0. So the argument is 0. So that means x of 0. So what is x of 0? X of 0 is the previous instant input. So when you fed previous instant, at the previous instant, when you fed x of 0, that one part, or you have extracted that and stored here. And that is the operation it is doing. Now what you understood? It's stored here. So it's stored here. Now it is releasing. Now it is releasing. So when it is releasing, here it is coming, getting multiplied by b1. So b1 x of 0, which is added with x of 1, the next sample, and multiplied by the b0. So giving you this part. And what is that part? That part is when you got the y of 0, that is the previous instant output. One, when extracted, one part of that was stored, and now it is actually extracted, or you can say it is basically you are bringing it back. So it was stored and you are bringing it back, and after multiplying with d1 and feeding at the input of the summer or adder, which as a whole is giving my y of 1. Similarly, y of 2 means b0 x of 2, b1 x of 2 minus 1 means x of 1. Now the first one sample actually is stored, which is kind of brought back now. Okay, here and here also the output, the same story. You are basically bringing it back here and adding and doing the operation. So in this way, basically this operation will continue. Fine. Now the point is here you are taking the output and feeding it back. Look at the direction of the arrow. Okay, taking the output and feeding it back. So it's kind of feedback. In the feedback system, what do you want to learn? I think in the first semester, feedback. So this is kind of a feedback system. So the output is being fed back to the system itself. So it's kind of feedback. But here, this is not the back. This is basically feed forward. So the input, or one part of the input, is basically feeding forward. You are feeding it through this path. This is another path actually. Look at this. This is one path. This is another path. So you are feeding, but feeding in the forward direction. Here, this is the direction of the arrow, but you are feeding, but feeding in the backward direction. So you are feeding it back to this path. But here you are feeding forward to this path. So it's going to feed forward, it's going to feed back. So depending on the arrow and all this kind of stuff. Now, suppose then, okay, this is okay. This is up to this it's okay. Now the next question is, my question is that suppose this equation of the mathematical representation, it represents that we have this xn x of n minus 1, that means the present instant input, the x of n means nth instant, in minus 1th instant. Okay, this is the past output. Okay, that means n minus 1th instant output, something like that in general. Okay, so in this way we can find this expression, or this mathematical expression actually gives you the difference, because you have yn minus 1, xn minus 1. This is in general called the difference equation, not the differential equation. It is a difference equation. Its counterpart in the continuous time domain will be simply the differentiation, and the summation will be the integration. So there you will get some kind of differential equation. Instead of it's kind of difference equation, you will call it a difference equation. There you will get the differential equation. So basically the concept is same. Now your task will be to develop this kind of system or representation of the system. So get used to with this kind of representation of system. which will basically deal with the continuous time domain signals. Then how to represent this kind of addition? If the addition will be simply the integration, difference and summation will be just simply the subtraction. Differentiation, and delay. How to represent the delay there in the continuous time case? How to represent the scalar multiplication and all those kind of stuff. That means that all these equivalent or analogous things in the continuous time domain, it is your task to find out and learn by yourself if you understand the concept here. So everything what is there written in terms of the addition, then it will be simply integration will be there, have to be done. What is written in terms of difference or something like that, there you have to follow the operation of differentiation. Okay, so in general you will get a differential equation there. So but the concept is same. Now the question is, even though these two kinds of, there also you will get two kinds of representation. One will be the symbolic representation, a block diagram representation, or this kind of signal flow representation here, and another will be the differential mathematical representation, like what you got here, a block diagram representation as well as a mathematical representation or the difference equation. Okay, now the question is, these two are equivalent, na? Basically giving you the same information. They either you represent it in the block in this kind of blocks with the help of blocks, or this kind of mathematical relation. You are basically conveying the same message. You are basically trying to give the same message. So or trying to depict or describe same digital system. Okay. Now then, can you identify just by looking minutely in these two types of representation, which are equivalent to each other, of course, is there any difference? Even though they are basically representing the same system. But as far as the mode of the representation is concerned, can you identify any basic difference between these two kinds of representation? Any basic difference?
So from the diagram, so you can describe the path of the signal. But from the
So, I'm not getting your voice. I'm not getting it. From the diagram, can you repeat? Hello? I can't hear
Sir,
you.
you hear me now?
No, I cannot hear anything from you.
Sir, can you hear you now? Can you hear please?
Sometimes I can hear, sometimes I cannot. So I cannot actually got the sense.
Can you hear me right now?
Yes, continue.
Sir, diagram, we can determine the path of the signal, but from the equation we can't.
Very good. Exactly. From the diagram, we can determine the path or the direction signals are flowing. We can determine these arrows are very important here. Exactly, right you are. So here these arrows are basically giving you the exact information, that is the direction along which the signal is flowing. Therefore, it is very much clear that along this direction is signal going, along this direction another path, along this direction it's after addition this. So all the directions are very much clear. So paths are very much clear. So from which end to other, which end it is flowing or going or something like that. But in this mathematical representation or this equation representation, it is not clear. You cannot say which one is the input, which one is the output, because here it is very much clear that this is the input, this is the output. But here from this expression you cannot say, because there is a hard and fast rule that yn will always be output, xn will always be input. I can change it. I can rearrange the terms. I can bring xn at this side and other terms at this side, then divide by and make this representation in any way whatever I want. Then from that, how one can get that what is the input, what is the output, how the signals are flowing, how the things are connected, something like that. This information cannot be captured. So that is why this path, these arrows are giving you the precisely. So it is this representation is a precise representation. This is precise and this is concise. Why it is concise? Because you need so many blocks, so many arrows, so many things to represent this. While on the other hand, you need minimum things to represent the same system. So it is concise but not precise. This is precise. Here you are precisely pointing or indicating the everything very minutely. So this representation is very precise. This is concise. That is the basic difference. Thank you very much. You are absolutely correct. আচ্ছা তুমি কে বললে তোমার নামটা কি আমি তোমাকে আইডেন্টিফাই করতে পারি
উদয় স্যার
উদয় থ্যাংক ইউ উদয় থ্যাংক ইউ ভেরি গুড অবজারভেশন ওকে ঠিক আছে তাহলে আজকে আপাতত এই অবধি থাক আর কন্টিনিউ করছি না আবার পরের দিন দেখা যাবে ঠিক আছে নাকি আরেকটু করবো আর 10 মিনিট
না স্যার এটা অনেকটা কভার করতে হচ্ছে
আচ্ছা ঠিক আছে আচ্ছা তোমরা একটু কানেক্টেড থাকবে আমি তোমাদের অ্যাটেন্ডেন্সটা নেব
ওকে স্যার
তোমাদের টেস্টের ডেটটা কবে যেন দিয়েছে আর একটু বলো তো আমি ভুলে গেছি মানে সিগন্যাল সিস্টেমটা কবে আছে গো 29th কি বার পড়ছে দাঁড়াও 29
সোমবার স্যার নেক্সট সোমবার
সেকেন্ড ধাপে আছে না সেকেন্ড ধাপে মনে হয় আমি যত দেখেছিলাম
হ্যাঁ স্যার সেকেন্ড হাফে
সেকেন্ড ধাপে আছে আমার এবার মনে পড়ছে আস্তে আস্তে তো সিলেবাস মানে তার আগে তো আর আমার কোনো ক্লাস হচ্ছে না আজকে তাহলে লাস্ট আর সিলেবাস তাহলে এই অবধি থাকবে আর কিছু করার নেই ঠিক আছে তো তাহলে আরেকটা পার্ট ভেবেছিলাম ওটা হবে না ঠিক আছে এভরি থাক তাহলে সিলেবাস আপাতত আর আচ্ছা তোমাদের পরীক্ষা কবে কবে আছে একটু বলবে আমাকে মানে আমি নেক্সট ক্লাসটা কবে নেব সেভাবে একটু প্ল্যান করে তো মানডে থেকে ওয়েডনেসডে ও বাবা তার মানে আমার বুধবার পড়ে যাচ্ছে ওর মধ্যে আচ্ছা বুধবার যদি আমি রাতে ক্লাস নিই তোমার তো পরীক্ষা হয়ে যাবে সেকেন্ড হাফে আমি সন্ধ্যাবেলা ক্লাস নিলে অসুবিধা নেই তো
হ্যাঁ স্যার কোনো প্রবলেম হ্যাঁ
ল্যাবের থিওরি নেই ও আচ্ছা বুধবার আচ্ছা তাহলে বুধবার দিন নেব না তাহলে বৃহস্পতিবার আমাকে একটা টাইম দিতে পারবে সন্ধ্যের দিকে
স্যার ওই দিন আমাদের অফলাইন ক্লাস
কতক্ষণ থাকে
স্যার আমরা স্যার
4:30
ওখান থেকে স্যার মাঝে মাঝে যাতায়াত করতে হয় স্যার তাহলে আমাদের বাড়ি ফিরতে ফিরতে অনেক দেরি হয়ে যায় স্যার
এমন একটা দিন বলো মানে ওই সপ্তাহে যে দিনটা তোমরা হ্যাঁ আমার কোনো অসুবিধা নেই শনিবার নেব কোনো অসুবিধা নেই শনিবার কখন নেব বলো টাইম বলো
কোন সময়
যে কোনো time, স্যার
যে কোনো সময়
সকালে কারণ রাত্রিরে আবার ডিএস এর ল্যাবের থিওরি হয়
কে
ডেটা স্ট্রাকচার ল্যাবের
ও
থিওরি হয়
ডেটা স্ট্রাকচার আছে ডিএস মানে আমি ভাবলাম কোনো টিচার সেই জন্য জিজ্ঞেস করলাম আচ্ছা সকালের দিকে আচ্ছা ঠিক আছে সকালের দিকে যদি হয় শনিবার কি তারিখ পড়ছে দাঁড়াও 4 তারিখ 4th ডিসেম্বর তাহলে তোমাদের 10টা থেকে 12টা হবে
হ্যাঁ
ঠিক আছে 10টা থেকে 12টা তাহলে আমি আর মেল করছি না কিন্তু একটু কমিউনিকেট করে দিও বাকিদের ঠিক আছে সিআর 4 তারিখ শনিবার 4th ডিসেম্বর 10টা থেকে 12টা সকালে একটু কমিউনিকেট করে দিও দাও
ওকে
ঠিক আছে আর সিলেবাস এই ক্লাস টেস্টের জন্য এটা তোমাদের অনলাইনে হচ্ছে কিন্তু এটা জানো তো
হ্যাঁ স্যার
ওকে আচ্ছা 301 অ্যাবসেন্ট 2 কি আদৌ আছে 303 4 5 6 306 7 8
Yes, sir.
308.
Yes, sir.
Okay. 309.
Yes, sir.
310.
Present, sir.
11. 311. Absent. 312. Absent. 313.
Yes, sir.
31. Okay. 4. 5. 6. 316. Absent. 320.
স্যার 319 স্যার উদয় আছি প্রেজেন্ট স্যার।
ও 319। আচ্ছা তুমি আজকে প্রথম?
আজ স্যার আমার ফার্স্ট ক্লাস এটা। আগের দিনের
ও।
ক্লাসের সময় স্যার আমি আর কি আমি দূরে থাকি তো তার জন্য আমি বুধবার দিন যাই কলকাতা।
তুমি কোথায় থাকো?
হ্যাঁ
না তুমি কোথায় থাকো?
আমি বাঁকুড়াতে স্যার।
ও বাঁকুড়াতে থাকো। তোমার পক্ষে তো প্রবলেম হয়ে গেল গো, এই অফলাইন
হ্যাঁ
অনলাইন।
স্যার আমি শিফট হয়ে যাবো এই ডিসেম্বরে শিফট হয়ে যাবো।
আচ্ছা 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 দাঁড়াও, তোমার কত বলে? 319।
319।
একটু দাঁড়াও, আমি একটু নোট করে নি। হ্যাঁ 319। তোমার নাম হচ্ছে উদয়। সারনেমের স্পেলিংটা বলো তো একটু।
SANNI
তাহলে নাই
GRAHI।
GRAHI, তাই তো?
হ্যাঁ হ্যাঁ
ওকে ঠিক আছে। আচ্ছা 401। আচ্ছা 320 আছো? 320 নেই। 401।
প্রেজেন্ট স্যার।
স্যার আমি 321।
321। ও তুমিও তাহলে নতুন?
হ্যাঁ স্যার।
দাঁড়াও 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 দাঁড়াও, এই তোমাদের ইনফরমেশন গুলো তো দেয়নি আমাদের কেউ, কারা নেই কারা আছে, তো খুব গন্ডগোল হয়ে গেছে। তোমাদের কোঅর্ডিনেটর কে গো? শম্পা ম্যাডাম তো?
হ্যাঁ স্যার।
কোঅর্ডিনেটরের সঙ্গে কথা হলে একটু বলো তো প্রপারলি
স্যার
ইনফরমেশন গুলো দিতে।
স্যার 320 অব্দি লিস্টটা আমার কাছে আছে।
না, আমার কাছে ছিল না। আগের দিন তো তোমরা আমাকে দুজনের নাম বললে না, যে 316
হ্যাঁ
320।
স্যার।
তারপরে আজকে ধরো
এবারে
উদয়
তারপরে-
এলো, 321 এলো, আবার ধরো ওপরের দিকে দেখছি তো অনেকেই নেই, সেগুলো
হ্যাঁ, স্যার।
প্রপারলি মানে এরকম ইয়ে হয়ে যাচ্ছে না, সমস্যা। 321 বলো, নাম বলো।
স্যার রাহুল চট্টোপাধ্যায়।
রাহুল
হ্যাঁ স্যার।
চট্টোপাধ্যায় লেখো।
হ্যাঁ স্যার, CHATTO।
আমি জানি, আমার স্যার নেই, অসুবিধা নেই।
ও আচ্ছা স্যার, বলছি আমরা যারা নিউ অ্যাডমিশন নিলাম স্যার, আমরা তো আগের আপনার ক্লাসগুলো করিনি, তাহলে স্যার আমরা ওইগুলো কিভাবে মানে রিক্যাপচুলেট বা ম্যানেজ করব?
দেখো আমার আগের ক্লাস বলতে আমি যে অনেক ক্লাস নিয়েছি আগে তা নয়। আমি নিয়েছিলাম প্রথম দিকে দুটো, তারপরে আমি প্রায় সম্ভবত 1-1.5 মাস মনে হয় নিতে পারিনি। মাঝখানে পুজো টুজো ছিল অবশ্য।
আচ্ছা।
তো তুমি যেটা করবে কি, যারা এই 4 ইয়ার্স বিটেক, তুমি তো বিএসসি বিটেক সম্ভবত,
হ্যাঁ।
3
হ্যাঁ স্যার।
321 যেহেতু, তো যারা 4 ইয়ার্স বিটেক সিআরকেই ধরো বলছি, ওর সঙ্গে একটু কমিউনিকেট করে নিয়ে যে একটু দেখে নেবে আমি কোন কোন জিনিসগুলো পড়িয়েছি। ওদের কাছে ডেফিনেটলি নোটস থাকবে বা স্লাইডস থাকবে, ঠিক আছে? ওখান থেকে একটু দেখে নেবে। আমি খুব বেশি কিছু পড়াইনি, সবই ওই একটু ইন্ট্রোডাকশন দিয়েছিলাম। হ্যাঁ, মেইনলি ওই স্যাম্পলিং ট্যাম্পলিং এর উপরই করেছিলাম, অ্যানালগ ডিজিটাল কন্টিনিউয়াস ডিসক্রিট এগুলোর উপর। খুব যে সেরকম খুব ডিটেলসে কিছু বলেছি তেমন নয়, যেটা মিস করে গেলে তুমি কন্টিনিউ করতে পারবে না এমন নয়। একটু দেখে নেবে তাহলেই হয়ে যাবে। ওকে, ওদের সঙ্গে একটু কথা বলে নিও। এটা প্রেজেন্ট
স্যার
ছিল।
ঠিক আছে।
স্যার কোন বইটা ফলো করব?
স্যার 324 স্যার।
বলছি 1 মিনিট, আমি এটা কমপ্লিট করে নিয়ে আসি। হ্যাঁ, এখানে অনেকগুলো ডিস্টার্ব হয়ে যাবে না, তাই বলছি। 321 রাহুল চট্টোপাধ্যায় হলো, ঠিক আছে? আচ্ছা, তারপরে আর কেউ আছো? 3
হ্যাঁ স্যার 324
324। আচ্ছা দাঁড়াও,
হ্যাঁ
324। বলো, নাম বলো।
Sir, Udayan Mondal, UDAYAN.
দাঁড়াও, উদয়ন ইউডি
AYAN.
মন্ডল।
হ্যাঁ,
মন্ডলের স্পেলিং কি লেখো? MON না MN?
MON.
MONDL, তাই তো?
হ্যাঁ স্যার।
আচ্ছা, আর কেউ 3 ইয়ার্স 3 ইয়ার্স বিটেক? আর কেউ নেই? ঠিক আছে, তাহলে আমি এবার 4 ইয়ার্সে গেলাম। 401
Present, sir.
6
Present, sir.
8
Present, sir.
411
Present, sir.
411 এর পরে হচ্ছে 416 416 absent 418 418 absent 19
Yes, sir.
20 420
Present, sir.
okay তারপর কত 425
Present sir.
427
Present, sir.
8 428 Orko absent Shayon 429
Present আছে
Present, sir.
মাইকটা পুরো
ও আচ্ছা অর্ক প্রেজেন্ট আছে আচ্ছা ঠিক আছে করে দিচ্ছি 429
Present, sir.
430
Present, sir.
32
Present, sir.
33
431 আমার
Present, sir.
ও 31 আছে মাঝখানে আমি মিস করে গেছিলাম না আচ্ছা 31 প্রেজেন্ট তাই তো 31 প্রেজেন্ট 32 ও প্রেজেন্ট আছে আচ্ছা 433
Present, sir. Present, sir.
ওকে 34 অর্পণ আছো absent আচ্ছা 35 শৌভিক
Present, sir.
36
Present, sir.
37
Present, sir.
38 আর কেউ আছো বাকি
স্যার 323 স্যার 323
323
হ্যাঁ
ও মানে 3 ইয়ার্সে আচ্ছা
yes
323 নাম বলো
দীপেন্দু ধর
স্পেলিং বলো
DIPY
DIPY
ENDU
ENDU
DU
হ্যাঁ
EHR
DHR ঠিক আছে তুমি আজকে প্রথম তাই তো
হ্যাঁ স্যার আমার ফার্স্ট ক্লাস এটা
আচ্ছা তোমরা কি তোমাদের অ্যাডমিশন কি দেরিতে হয়েছে নাকি
স্যার এই সামনের 20 তারিখ হয়েছে অ্যাডমিশন
ও ওরে বাবা ঠিক আছে আর কেউ বাকি আছো আর কেউ নেই তাই তো ঠিক আছে আচ্ছা এইবার বলো কি বলছিলে তোমরা
স্যার বলছি কোন বইটা ফলো
বই
করব আর
আচ্ছা বই হ্যাঁ বইয়ের কথা বলি বই তোমরা যেটা ফলো করতে পারো কোনো একটা পার্টিকুলার বই ফলো করলে আমাদের কিছু হবে না কারণ বিভিন্ন জায়গা থেকে করে পড়ানো হয় তো এই কোর্সটা আমি তোমাদের 4-5টা নাম বলছি যেটা যেরকম পাবে অ্যাভেলেবল পড়তে পারো কোনো অসুবিধা নেই যেমন প্রথম যে বইটা আমি ফলো করি সেটা হচ্ছে বিপি লাঠি একটা বই আছে ঠিক আছে বিপি লাঠি সিগন্যালস এন্ড সিস্টেমস বিপি লাঠির কিন্তু অনেক বই আছে সেগুলো পার্টিকুলারলি আমি বলে দিচ্ছি ওই জন্য সিগন্যালস এন্ড সিস্টেমস আর একটা বই আছে ওপেনহ্যাম আমি অথরের নাম বলছি এটা ওপেনহ্যাম ওটাও সিগন্যালস এন্ড নাম সবই এক সিগন্যালস এন্ড সিস্টেমস ওকে তো আরেকটা আছে দেখবে আরো অনেক অনেক বই পাবে তোমরা এছাড়াও আছে সম্ভবত ওই দাঁড়াও দেখবে একটা বই আছে রমেশ বাবু ঠিক আছে ওই বইটাও দেখতে পারো কিন্তু ওখানে একটু কেয়ারফুল থাকবে ওখানে কিছু কিছু মিস্টেকস আছে মানে মিস্টেকস মানে টেকনিক্যাল মিস্টেকস বলছি না মানে প্রিন্টিং মিস্টেক তো সেগুলো একটু কেয়ারফুলি পড়তে হবে যদি কেউ পড়ো ওই বইটা এছাড়া একটা বই আছে হিসাব আনন্দ, আমি অথরের নামটা এই মুহূর্তে মনে করতে পারছি না, আনন্দ বলে আর কি। তো যদি ডিপার্টমেন্টে যাও একটু সার্চ করে দেখো, আনন্দের একটা বই আছে সিগন্যালস এন্ড সিস্টেমস এর, ওটাও ভালো, ওখান থেকেও পড়তে পারো। ঠিক আছে, এরকম 4টে বই আপাতত মনে পড়লো। এই 4টে বই দেখো একটু ঘুরিয়ে ফিরিয়ে, যেটা যেরকম যেভাবে অ্যাভেলেবল থাকে। ঠিক আছে, তারপর টাইম টু টাইম তো যেভাবে যা পড়ানো হচ্ছে সেগুলো এখান থেকে পেয়ে যাবে।
আচ্ছা, মেইন টপিক যেগুলো আপনি কভার করেছেন এই প্রিভিয়াস লেকচারে, সেগুলো একটু বলুন।
সেগুলো এই যে বললাম বইয়ের নাম।
না বইয়ের নাম না, মেইন টপিক গুলো যেগুলো কভার করেছেন এখনো পর্যন্ত।
ও টপিক গুলো যেগুলো কভার করেছি, আচ্ছা আচ্ছা, টপিক গুলো যেগুলো কভার করেছি সেগুলো প্রথমে হচ্ছে তোমার ছিল বেসিক্স অফ সিগন্যালস এন্ড সিস্টেমস। তার মধ্যে তোমার পড়ছে মেইনলি কন্টিনিউয়াস টাইম ডোমেন সিগন্যাল সিস্টেম, ডিসক্রিট টাইম ডোমেন সিগন্যালস এন্ড সিস্টেম, তাদের ডেফিনেশন, তাদের রিলেশন, হাউ টু কনভার্ট কন্টিনিউয়াস টাইম টু ডিসক্রিট টাইম ডোমেন। ঠিক আছে, তার মধ্যে পড়ছে স্যাম্পলিং, কোয়ান্টাইজেশন। স্যাম্পলিং এন্ড কোয়ান্টাইজেশন সম্বন্ধে আমি খুব ডিটেলস বলিনি, যেটুকু তোমাদের কোর্সের জন্য আছে, খুব ডিটেলস বলছি না ওই জন্য বারবার, মানে ব্রিফ ইন্ট্রোডাকশন আর কি, জাস্ট কনসেপ্টটাকে ইন্ট্রোডিউস করেছিলাম। আর একটা দুটো মানে এক্সাম্পল দিয়েছিলাম, স্যাম্পলিং বলতে কি বোঝায়, কোয়ান্টাইজেশন বলতে কি বোঝায়, এটসেট্রা। সো দি স্যাম্পলিং রুল ফলো Nyquist criterion, if not followed then what happens, এটসেট্রা। এই পার্টগুলো মেইনলি পড়িয়েছিলাম আর কি প্রথম দিকে। তারপরে লাস্ট ক্লাসে যেটা করলাম সেটা হচ্ছে যে রিপ্রেজেন্টেশন অফ কম্পোজিট সিগন্যাল ইন টার্মস অফ ডিফারেন্ট এলিমেন্টারি সিগন্যালস। ঠিক আছে, তো সেটা করলাম আজকে। তারপরে ডেল্টা ফাংশন, ইন দিস কনটেক্সট ইন্ট্রোডিউস দ্য কনসেপ্ট অফ ডেল্টা ফাংশন, ইটস ডেফিনেশন, ইটস প্রপার্টিজ। এন্ড তারপরে আজকে তোমার ডেল্টা ফাংশনের প্রপার্টিজ এর রেসপেক্ট হয়ে আজকে যে এক্সপ্রেশন গুলো করালাম সেগুলো। তারপরে আজকে তো যেটা করালাম সেটা দেখতেই পেলেন, এই তো ব্যাপার মোটামুটি।
ওকে স্যার, থ্যাংক ইউ।
ঠিক আছে, ওকে। আর যদি কারোর কিছু প্রশ্ন না থাকে তাহলে আমরা আবার 4 তারিখে মিট করছি 10টা থেকে 12টা। ঠিক আছে,
ওকে স্যার।
ওকে, থ্যাংক ইউ।